Master the art of dynamic programming by learning to break complex challenges into simple, reusable subproblems. This course features step-by-step animations that bring abstract logic to life, showing you exactly how data flows through tables and recursion trees in real time. Develop a powerful visual intuition for optimization so you can solve even the toughest algorithmic puzzles with ease. Sheldon created this course.
Dynamic programming is one of the most powerful tools for solving coding interview problems, but it can feel overwhelming at first. In this video, we'll break down the main DP patterns step by step in plain terms and with clear visual examples so you can actually understand what's going on and start solving DP problems with confidence. Hi, I'm Sheldon, an ex-Googler with 10 years of experience, and I help you prep for coding interviews on the Algo Monster platform. Good news! You don't need to memorize hundreds of problems to get good at dynamic programming. You just need to master a small set of patterns. Most DP problems are variations of the same ideas, and once you recognize those patterns, new problems become much easier to solve. So that's what we'll concentrate on, but we'll start from the fundamentals and build up from there, one concept at a time. Let's look at a popular problem. There is a staircase with n steps. You are at the bottom and want to reach the top, and there are two possible moves. Climb one step at a time or jump 2 steps at once. And we need to count how many different ways there are to reach the top. To understand it better, let's look at a simple example. A staircase with 3 steps. What options do we have? Here we can climb 1 step 3 times in a row, or take 1 step, then jump 2. Or you can jump 2 at once and then take 1 step. But when the number of steps grows, for example to 10, counting the options by hand becomes difficult, so it's better to write code that quickly calculates all possible paths. Where do we start? Let's think about how you can get to a step. First, consider the simplest cases. For the first step, there is only one way to get there. You take 1 step. But for the second step, there are already 2 ways. You either take 2 single steps, or you make 1 big jump straight to the second step. And now let's move on to the third step and just continue with the paths we already know. At this point, we already have all the ways that lead to step 1 and step 2. So each of those paths can be extended to reach step 3. Paths that led to step 2 can add 1 more step up, and paths that led to step 1 can be extended with 1 jump directly to step 3. So nothing new really appears here. We're only extending existing routes. That means the total number of ways to reach step 3 is 1 plus 2. So it's 3 ways in total. In other words, all paths that end at step 2 are already counted. And when we add 1 more step to reach step 3, we don't create a new path. It's the same path, just extended by 1 step. The same idea applies to the path from step 1 to step 3. We simply continue it without creating anything new. Now let's see what happens with step 4. Here, the same logic of extending existing paths applies again. First option, we reach step 4 through step 3. Everything we already counted for step 3, all 3 routes, can take 1 more step to reach step 4. These are not new paths, just the same routes extended to the top of the staircase. And the second option, we jump directly from step 2 to step 4. For step 2, we already have 2 different paths, and we add 1 jump to each of them to reach step 4. Once again, we're just extending the paths we already had. In the end, all paths found for the 2 previous steps are simply extended 1 more step forward. And for step 4, we get 3 ways through step 3 plus 2 ways through step 2. Total, 5 ways. So the idea is this. We only count distinct routes for the 2 previous steps and then extend them. The same path can never be counted twice. We only expand it by 1 more step or jump. If we generalize this rule, we get that the number of ways to reach step n is the sum of the number of ways to reach step n minus 1 and step n minus 2, simply because you can only get to step n from the 2 previous ones. Now that we've derived this rule, let's implement it in code. But let's start with the simplest situations first. If you need to reach the first step, so n equals 1, there's only one option. You take 1 step. That's our first base case. Next comes the second step. Here there are 2 possible ways, either 2 small steps or 1 big jump. This is our second base case. And for all other steps, we use the rule we've already discovered. The number of ways to reach step n is the sum of the ways to reach steps n minus 1 and n minus 2. Now, the natural question is, how do we actually get these 2 numbers? This is where recursion comes in. The function simply calls itself. First, it asks, how many ways are there to reach step n minus 1? And calculates it recursively. Then it asks the same question for step n-2. Since the function itself knows how to compute the number of ways for any given step, the values it returns are exactly what we need. All that's left is to add them together. But to really see how this works, let's walk through the recursion step by step. Let's start with step 3, that is n=3. We call the function and go through the first two checks. 3 is neither equal to 1 nor to 2, so we move on to the formula. To compute the number of ways to reach step 3, the function first calls itself for step 2, and this immediately returns a value because step 2 is one of our base cases. Then the function calls itself for step 1, and that also immediately returns a value, since step 1 is a base case as well. Now we have both numbers, so we simply add them together. 2 plus 1 gives us 3, and that's exactly the value the function returns. Everything checks out. Now let's go one step further and look at step 4. If n=4, the function again follows the same logic, just one level deeper. First, it calls itself for step 3. Inside that call, the function again needs the values for steps 2 and 1, both of which are base cases. For step 2, the answer is 2. For step 1, it's 1. Adding those gives us the result for step 3, which is 3. That's the first part. Next, the function also needs the number of ways to reach step 2, but since that's a base case, we already know the answer is 2. Now we can apply the formula for step 4, 3 plus 2. So the result is 5 ways to reach step 4. And once again, everything works exactly as expected. But here's the problem. What happens if we call the function for step 40? Well, the calculation will take a very long time. But why does that happen? To understand this, let's look at the recursion tree for step 6. If you look closely, you'll notice that the number of ways to reach step 3 is calculated multiple times. It's needed when we compute step 4. It's needed again for step 5. And since step 5 itself depends on step 4, that same calculation shows up there again. The core issue is that our function doesn't remember any previous results. So every time the calculation for step 3 appears somewhere in the recursion tree, the function recomputes it from scratch. The exact same work is done over and over again. As n gets bigger, the recursion tree grows larger and larger, and the number of these repeated calculations explodes. And this leads to the most important point. The number of recursive calls grows extremely fast. In fact, the time complexity here is O of 2 to the power of n. That means that even for n=30, we already end up doing about 1 billion repeated computations. Okay, so we found the inefficiency, but the real question is, how do we avoid recalculating the same values over and over again? What if the very first time we compute the number of ways to reach a step, we simply store that result somewhere? Then every next time we need it, we can just reuse it instead of recomputing everything. If we want to store results, we obviously need some kind of storage. So what should it look like? Think about it this way. When we compute the number of ways to reach step 3, we'd like to save that value. And the next time recursion reaches step 3, we want to immediately return that saved result. The step number works perfectly as a key, and the number of paths is the value. That makes a hash map a perfect fit here. Now let's walk through how recursion changes with this idea in place. For example, when we want to compute the answer for 5 steps, we start with n=5. Before doing any real work, the first thing we do is check the hash map. Maybe there's already a stored result for step 5? There isn't. It's still empty. So we continue as usual and break the problem down into steps 4 and 3. We move to step 4. Again, we check the hash map. Still empty. So we break this down further into steps 3 and 2. Next, we reach step 3. Once again, nothing is stored yet, so we need the values for steps 2 and 1. Step 2 is a base case. We know there are exactly 2 ways to reach it. The same thing happens with step 1. It's also a base case, so we just get it instantly. Now we finally have everything we need to compute step 3. We add the values together, get the result, but now, before returning, we store it in our hash map, because it's a new value we calculated. And up to this point, everything looks very similar to what we had before. But now comes the important difference. Look closely. We move back up to step 4. We already have the value for step 3, and we also need the value for step 2. When recursion reaches step 2, we instantly return the result because it's the base case. We add the 2 values, store the result for step 4 in the hash map, and return it. And now comes the best part. We're back at step 5. We already have the value for step 4. Now we also need the value for step 3. Normally, this is where recursion would again break step 3 into steps 2 and 1, but this time it doesn't. We check the hash map, see that step 3 is already there, and instantly return it. No extra recursion at all. See what's happening? Instead of recomputing everything from scratch every time, we store intermediate results and reuse them. This saves a massive amount of time and resources. For example, if you look at the recursion tree for 6 steps, you'll notice that all those duplicate computations simply disappear, because every value is computed only once. And the larger n gets, the more powerful this optimization becomes. Now let's summarize what the code does conceptually. First, we create an empty storage, a hash map, where we'll keep all computed results. Then, inside the function, the very first thing we do is check that storage. If the answer for this step was already computed, we return it immediately and stop. If not, we check the base cases just like before. If those don't apply, we compute the number of ways recursively using our formula. But now there's one extra step. After computing the result, we store it in the hash map using the step number as the key. That way, the next time we need this value, we can instantly reuse it. Only after that do we return the result. And what we've just done is called memoization, a technique where we store the results of previous function calls so we don't recompute the same thing when the same input appears again. In other words, memoization is recursion with memory. We still solve the problem top-down, but every answer we discover gets saved, so future calls can just grab it from storage instead of doing the work again. In practice, memoization is one of the fundamental and most powerful techniques in dynamic programming. It shows up in a huge number of problems and can dramatically speed up solutions. Without memoization, this algorithm has exponential time complexity, but with memoization, the time complexity drops to linear, O of n, because we compute each step only once. And since there are only n steps, the total work is linear. The memory usage is also O of n. We store at most n values in the hash map, and the recursion depth will never exceed n either. Because of this, memoization is a core technique used in many algorithms and is extremely common in interviews. But now let's pause for a moment and ask an important question. Do we really need to use recursion here? Can we solve this problem with a loop? If you think about it, it really looks like we're naturally moving through the steps in order. We start with the first step and compute the number of paths. Then we move to the second step and do the same. Then for the third step, we already have everything we need, so we can just apply the formula. And then we keep going like that. In other words, it seems we can simply move from one step to the next in a loop. We already know the formula, but for this to work, we need to store the results of the previous steps somewhere. And the simplest option is an array. Each index in the array would represent a step number, and inside that cell, we store the number of ways to reach that step. Then we just move forward along the staircase in a loop, take the last two values, apply the formula, and store the result in the next cell. And we repeat this until we reach the final step. And there's no recursion here, no cache checks, no call stack, just a clean bottom-up loop where every step depends only on the previous two results. Let's walk through how this works step by step using the example with 5 steps. First, we create an array and immediately fill in the base cases. At index 1, which is step 1, we store one path. At index 2, which is step 2, we store 2 paths. Now we move forward. For step 3, we look at step 2 and step 1 and add those values together. 1 plus 2 gives us 3, so we store that in the third cell. Then for step 4, we take the value from step 3, which is 3, and add the value from step 2, which is 2. That gives us 5, so we store it. And then for step 5, we take the value from step 4, which is 5, and add the value from step 3, which is 3. That gives us 8, and we store it too. And that's it. The answer is now sitting in the last cell of the array. Now let's summarize what this solution does conceptually. First, we create an array, a table where we store already made answers for each step from bottom to top. For steps 1 and 2, we immediately write down the known base cases. Then we run a simple loop starting from the third step and moving upward. On each iteration, we take the 2 previous values from the array, add them together, and write the result into the current position. And at the very end, we return the last value in the array. That's the number of ways to reach the required step. This loop-based approach also has a name, tabulation. Tabulation is a technique where we explicitly fill a table of results step by step. First the base cases, and then gradually build up to the final answer using previously computed values. It's one of the fundamental and very powerful techniques that appear in a huge number of problems. It gives predictable performance, avoids recursion entirely, and has linear time complexity, and the memory usage is also O of n since we store one value per step. Now let's compare these two approaches. The main difference is simple. Memoization is recursion with memory. We solve the problem top-down and store intermediate results in a cache. Tabulation, on the other hand, is a bottom-up loop. We fill an array step by step, from the start all the way to the final answer. There's also a difference in how memory is used. Memoization needs memory for the cache and for the recursion call stack, whereas tabulation only needs the array, which usually makes it more efficient. So, which approach should you choose in a real problem? If you're working on a problem where the order of computations doesn't really matter, a top-down approach is often a great fit. Recursion naturally computes all the intermediate values you need, and you don't have to think too hard about the order yourself. This works especially well for partition-type problems. For example, when you need to split a string into parts or divide an array into groups. In those cases, recursion with memoization is very convenient, because it automatically explores and computes all the inner partitions. With a bottom-up approach in problems like that, it's often not obvious which partitions should be computed first in order to calculate the rest. Figuring out that order can make the solution much harder. On the other hand, when you use the bottom-up approach, it's usually easier to analyze the time complexity. You can clearly see the cost of filling the table of intermediate results, and loops tend to make this more visible than recursion. There's another important benefit as well. With a bottom-up solution, you never risk a stack overflow, because there's no recursion involved. So if you can clearly see an order in which intermediate results can be computed one by one, bottom-up is usually the best choice. But if the order is unclear or hard to reason about, top-down is often the better option to start. Now let's apply this comparison to our staircase example. Here, we need all steps from one up to the final one. There are no unnecessary subproblems. And we also know the exact order in which everything should be computed, bottom-up. And the code itself is much simpler too, just a loop instead of recursive calls and checks. So for this staircase problem, tabulation really wins on all fronts. Memoization is great when recursion fits naturally or when not all subproblems are needed. But here we have a clean sequence, a classic case for tabulation. We fill the table once from bottom to top and we're done. Fast, simple, no extra checks. That said, if you personally find the recursive solution easier to understand or to come up with, it's completely fine to use that approach in an interview. Now let's practice on the AlgoMonster platform and solve one more popular problem using the techniques we've just learned. It's called the nth Tribonacci number, and basically it's an extension of a classical Fibonacci sequence problem, where each next number in the sequence is the sum of two previous numbers. But here, in the Tribonacci problem, each next number is the sum of not two, but three previous numbers. So to get the nth number in the sequence, you'd need to add numbers n-1, n-2, and n-3 together, and the Tribonacci sequence always starts from these three numbers. The 0 element is 0, the first is 1, and the second is also 1. So given the nth Tribonacci element number, we need to find its value. For example, if n equals 3, we just use this formula, adding all the previous three elements, the second, the first, and the 0th. They're given in the problem statement, so we'd get 2 in total, and this is the answer for n equals 3. But if n equals 4, then we'd need to add the third, the second, and the first elements now. Looking at their values, we'd get 4 in total. And in general, we need to write the code that returns the answer for any n. And this problem looks quite similar to our staircase problem. We even have the formula here, where it's clear that every next element depends on the previous ones. So to find the nth element, we first need to find those three. And we could do that using any approach we've learned. We could find it recursively, for example, and use memoization to optimize it. Or just like here, we could create an array of n elements, store the first three as they're given, and then move left to right, calculating each next element using the formula we have. Classic bottom-up approach. However, just like in the staircase problem, we see that each next element depends on only three previous ones. So on each step, we don't need elements before those three, and that means we don't need to store an entire array. We can just have three variables storing the values of the previous elements, and update them on each next step. We'd initialize them with the first numbers in the sequence, 0, 1, and 1, and then we'd use the formula to calculate the next number. After that's done, we'd update the variables, so they contain the last three elements in the sequence, 1, 1, and 2, because we've just found a new one, and then we'd do the same until we reach the nth element in the loop. With this approach, we'd need to start from the first elements of the sequence and move all the way to the nth element to calculate it eventually. That means we have O of n time complexity. But for the space, we always store just three variables, never more. That means our memory usage is constant, giving us O of 1 space complexity. This is the optimal solution for this problem. Let's write the code for it. We'd have a function that takes one argument n, the Tribonacci number we need to return. First, we have our base cases. From the problem statement, we know that the 0 element is always 0, so we can write them. Besides, we know that the first and the second elements in the sequence are 1s, so we can add this base case too. Then, if we got a bigger n, we need to use our formula to calculate its value. Following our approach, we create 3 variables and initialize them with the values of the first 3 elements in the sequence, 0, 1, and 1. Then we need to calculate each next element in sequence using our formula until we reach the nth position. For that, we can start a loop from the 3rd position until n plus 1. Inside, we just use our formula to calculate the next element based on the 3 previous ones. But then we need to update our variables so we can calculate the next elements later. For that, it's convenient to use tuple assignment in Python. Basically, we say here that t0 gets the value of t1, t1 becomes t2, and t2 becomes the result of our formula. After the loop completes, the t2 variable will contain the nth element value, because we save the result of the formula in this variable on every iteration. So we just return this value, and this is our solution. Let's run the test to see if we solved it correctly, and it's perfect. There are plenty of other problems and their solutions available on the AlgoMonster platform. Click the link in the description to practice and easily prep for your coding interviews. Okay, so we figured out how many ways there are to climb to the nth step. But now let's change the problem slightly. What if every step costs money, and instead of just reaching the top, you want to do it for the minimum possible price? This leads us to a very popular problem called min-cost climbing stairs. And you'll see that it's solved in almost the same way as the problem we just looked at. In this problem, you're given an array called cost. Each element in this array represents the price you pay when you land on a particular stair. Land on stair 1, you pay that amount. Land on stair 2, you pay that amount, and so on. You're allowed to start climbing from either stair 0 or stair 1. From any stair, you can move up to the next stair or jump over one stair, just like in the previous problem. But now the goal is slightly different. You don't just want to reach a stair, you want to reach the very top of the staircase, the floor, and you want to do it with the minimum possible cost. So the task is to find the minimum cost needed to climb all the way to the top. Let's look at a simple example. Suppose we have 3 stairs. Stair 0 costs 10, stair 1 costs 15, and stair 2 costs 20. That's our cost array. Your goal is to end up at the very top. In other words, to reach the floor. The floor itself is not part of the array because it's no longer a stair. So what options do we have? One option is to start from stair 0 and pay 10. From there, you jump over one stair and land directly on stair 2 paying 20. Then you take one more step and reach the floor. The total cost of this path is 10 plus 20, which gives us 30. Another option is to start from stair 1 and pay 15. From there, you jump over one stair and immediately reach the floor. This path costs just 15, and that's the answer to our problem because we're looking for the minimum possible cost. There are a few other possible paths here as well, but all of them end up being more expensive. So in this case, 15 is the best cost we can get. One important thing to notice here is this: we do not pay for landing on the floor. We only pay for the stairs we land on inside the array. Let's recall how we previously counted the number of ways to reach stair n. We said that you can reach stair n either from stair n-1 or from stair n-2. So ways of n equals ways n-1 plus ways n-2. Now the goal is different. We no longer care about the number of ways, we care about the minimum cost. But here's the key point. The transition logic stays exactly the same. You can still reach stair n in only 2 ways, either from stair n-1 by taking one step, or from stair n-2 by jumping over one stair. So structurally, nothing changes. The only real question now is this: how do we choose the cheaper of these 2 options? It turns out that just like in the previous problem, we can create an array where we store an intermediate value for each stair. The difference is that before we were storing the number of ways, and now we're going to store the minimum cost to reach each stair. Let's call this array min cost. Why do we need it? Because in this problem, once again, every next result depends on the previous ones. You can only reach a stair from lower stairs, which means we first need to know the minimum costs of those lower stairs. So once again, we need a place to store previously computed results. An array fits perfectly here. The index represents the stair number, and the value represents the minimum cost to reach that stair. Why does this work? Because we already know the minimum cost for stair 0. It's just its own price since that's where we start. So we can put in the array straight away. It's a base case. The same goes for stair 1 because we're allowed to start there directly as well. So its value can also be written into the min cost array right away. Now we can compute the minimum cost for stair 2. Watch closely. We We know that we can come to it only from stair 1 or from stair 0. These are the only two possible options. But we need to minimize the cost to the top. So which of these two options do we choose to get to the stair 2? Well, the cheapest one. We just look at these two costs and choose the minimum of those. But then, because we jump on the stair 2 now, we need to add it 2 to the total. Its price is known from the cost array, so we just add it to the minimal cost we chose from the previous two options. And it gives us the minimal cost to get to the stair 2, so we store it in the array. Then we do the same for stair 3. Its cost is known, and the minimum costs for the previous stairs are already computed. We choose the minimal one, add the stair cost, and we get the total minimal cost for stair 3. And then step by step, always relying on values we've already computed, we calculate the minimum cost for every stair and store it in our array for future use. This is the classic bottom-up approach. We start with the base values and gradually build up to the final result. As a result, we end up with the min-cost array that makes solving the problem straightforward. We simply take the minimum cost from the last two stairs, because from either of them, we can reach the floor. This is very similar to the previous problem, and that's exactly the power of recognizing patterns. Let's generalize the approach. Let min-cost n be the minimum total cost needed to step onto stair n, starting from the beginning. Now, where could you have come from to reach stair n? You could come from stair n-1. In that case, you've already paid the minimum total cost to reach stair n-1. Or you could come from stair n-2. Then you've already paid the minimum total cost to reach stair n-2. Which option is better? The cheaper one. So we take the minimum of those two values, and then we also add the cost to reach the stair n from the original array of costs. Now that we've figured everything out conceptually, let's translate this idea into an actual solution. We start by defining a function. As input, it receives the cost array, which contains the prices for each stair. This is exactly what the problem gives us. For convenience, we first store the length of this array. This tells us how many stairs there are in total. Next, we create the min-cost array. This is where we'll store the minimum total cost required to reach each stair. Now come the base cases. Just like we discussed earlier, the minimum cost to reach stair 0 is simply its own price. After all, we're allowed to start by stepping on it directly. The same idea applies to stair 1, so its price can also be written into the array right away. After that, we compute the remaining values. We go through the stairs starting from stair 2 and move forward, one stair at a time. For each stair, we apply our formula. We take the cost of stepping on the current stair and add the smaller of the minimum costs for the two previous stairs. As the loop runs, it computes the minimum cost for stair 2, then for stair 3, and so on until the entire min-cost array is filled. Each new value depends only on the two values before it. Once we're done, the last two cells in the min-cost array contain the minimum cost of stepping on the last two stairs, and those are exactly the stairs from which we can jump to the top floor. So to get the final answer, we simply take the smaller of those two values. And that's our solution. Now let's evaluate the complexity of this solution. First, the time complexity. We run a single loop that starts at stair 2 and goes up to the last stair. That's a straight linear pass, so the time complexity is O of n. Now the space complexity. We create the min-cost array, and it has exactly as many cells as there are stairs. Because of that, the space complexity is also O of n. That's already pretty good, but we could actually make this algorithm even more efficient. Let's take a closer look and see where there's still some inefficiency. Look carefully at the formula we use inside the loop. To compute the minimum cost for stair n, we only need two values. The minimum costs for stairs n-1 and n-2. That's it. We don't need all the previous values. We don't need half of the array. We need exactly two numbers. And think about what happens to min-cost 0 once we get to, say, stair 5. Nothing at all. We used it long ago, and after that, it never comes up again. So what's really happening here is this. We're storing a whole array of values, but in practice, at any moment, we're only using the last two, which leads to an obvious question. If we only ever need two values, why are we storing the entire array? So what if we remove the array entirely and use just two variables instead? One variable will store the minimum cost to reach the previous stair, and the other will store the minimum cost to reach the stair before that. We initialize these two variables in exactly the same way as before, using the costs of stair 0 and stair 1. Then we start moving forward through the staircase. Inside the loop, we compute the new value using the same formula as before. The only difference is that now we're taking the previous values directly from our two variables instead of reading them from an array. And after computing the new minimum cost, we update the variables. The first variable takes the value of the second one, and the second variable takes the new cost we just calculated. This way, at every moment, we're keeping track of the last 2 stairs we've reached, and those are the only values we ever need. Once we're done, we return the minimum of these 2 values, exactly like before, because from either of those stairs we can reach the floor. And the time complexity of this solution stays exactly the same, O of n. We still have a single loop that goes through the stairs, but the space complexity is now different. Instead of storing a whole array, we only use 2 variables. That means the space complexity drops to O of 1, constant space. So we reduced memory usage from O of n to O of 1 without losing any speed. That's exactly what we want. But now let's step back and see when this solution logic applies in general, because that's the second problem already, which we solved similarly. Look at what this problem and the earlier number of ways problem have in common. First, the state depends on a fixed number of previous states. In our case, it's just 2, n-1 and n-2. Second, the transition is always the same. It doesn't matter which stair you're on, the formula never changes. And third, the memory can be optimized. Since we only ever need the last 2 values, there's no reason to store the entire array. This is what we call a constant transition, a transition that depends on a constant number of previous states. It's one of the fundamental patterns in dynamic programming, and as you've just seen, very different problems can often be solved in almost the same way. The formulas may look slightly different, but the underlying logic is exactly the same. That's the real power of patterns. You don't need to memorize solutions to every problem out there. If you understand just a handful of core patterns, you can solve a huge range of problems. And next, we'll go through 5 more key patterns, just as simply and clearly as this one. So keep watching. But first, let's go to AlgoMonster and solve a very popular constant transition problem. It's called House Robber, and here we're playing the role of a robber who plans to rob houses along a street. Each house has a certain amount of treasure in it, but the constraint is that we cannot rob 2 adjacent houses. So we need to figure out the maximum amount of money we can get from those houses without breaking this constraint. Here we're given an array of integers representing the amount of money of each house, and basically we need to maximize the sum of non-adjacent elements. The phrase maximize the sum is already a sign that this is a DP problem, but here we need to figure out the formula ourselves. How do we do that? So what if we create an additional array where in each cell we will store the maximum sum we can get if we rob all the houses from the first to the current one. Then for the first one we just store its value because there are no houses before that, and for the second we choose the maximum between it and the previous house, because if the previous one is better then we cannot rob the adjacent one, or vice versa, so we take the best option possible here. These are base cases, but then when we move further along the street and look at any house deciding if we need to rob it or not, we also have only 2 options: break into that one or skip it because an adjacent one may be better. So if we're currently looking at the third house with the value of 9, then we could skip it and bear the same sum we had in the previous cell, which is 7. Or we could rob the one before that and now rob the current one too. Which is better? The maximum one. 2 plus 9 gives us 11, so we definitely want to use that one. And moving along we have the same choice. Use just the previous one or the one before that plus the current. And then we just take the maximum of these 2 options. So that's basically our formula. We're choosing from the 2 previous sums, but add the current element to the non-adjacent one. Then in the last element of our array, we'll eventually have the maximum sum of all the houses. And this is our answer. If we solve it exactly this way, then we'd need to create an array of n elements, which would give us O of n space complexity. And then we'd go over all the elements from 0 to n, which also has O of n time complexity. However, we can again optimize the approach and use just 2 variables to store the last 2 sums, as those are the only ones used in the formula. That would allow us to have O of 1 space complexity. So let's implement this solution. I'll save the length of the houses array in the variable n for convenience. Then we need to cover a couple of base cases. If the array length is 0, then the answer is obviously 0 too. Or if there are only 1 or 2 houses in the array, we can just choose the maximum element because there are no other combinations. For any other array, we need to implement our algorithm. First, the DP base cases. We save the value of the first house in the array, and we take the maximum of the first 2 houses and save it in a variable too. That's the values we'll start calculating the next sums from. Then we need to go over the rest of the houses. So we start a loop from index 2 till the array length. And inside, we just apply our formula and change the variable values for the next iteration. In the end, the second variable contains the final sum, which we return from the function. Now let's run the test to check if our solution is correct. And that works. Awesome. You can solve this problem yourself if you want. Just click the link in the description. Okay, so we've learned how to climb a staircase. We counted paths and we counted costs. But there was one important limitation. We were always moving in just one direction, upward. One stair or two, but never anything else. So what happens if we're allowed to move in more than one direction? And what if, instead of a staircase, we're dealing with an entire grid? This brings us to the next dynamic programming pattern, and you'll see that it's solved in a very similar way to everything we've already learned. Here's a grid, a regular table made up of cells. It has m rows and n columns. You start in the top left corner, and your goal is to reach the bottom right corner. There's just one rule. You can move only to the right or downward, no moving left, and no moving up. So the question is simple. How many unique paths are there from the start to the finish? This is a very popular problem called unique paths, and it should already sound familiar. In our first staircase problem, we were also counting the number of paths. So now, with that experience, this one will be much easier to understand. Let's look at a simple example, a 3x3 grid. That gives us 9 cells in total. We start in the top left corner and want to reach the bottom right corner. So what options do we have? One option is to go all the way to the right first and then all the way down. That's one path. Another option is to go all the way down first and then all the way to the right. That's a second path. Or we can alternate our moves. Right, down, right, down. That gives us a third path. And there are several other combinations like this. In fact, for a 3x3 grid, there are exactly 6 unique paths. But now comes the real question. How do we count this for any grid? For a 5x5 grid? Or for a 10x10 grid? Clearly, brute forcing all possibilities by hand isn't an option. We need a proper algorithm. Now look closely and think back to the staircase problem. There, we said that you can reach stair n either from n-1 or from n-2. And here, what about a cell in the grid? From where can you reach it? Either from the cell on the left, if you move right, or from the cell above, if you move down. There are no other possibilities. The rules of the problem simply don't allow anything else. So the logic is exactly the same. The number of paths to the current cell is equal to the sum of the number of paths to the neighboring cells from which you can reach it. If you've already reached those neighboring cells in different ways, you just continue those paths to arrive at the current cell. Then you add all those possibilities together, and that's your result. The only real difference is this. Instead of steps from the previous problem, we now have 2 neighboring cells, the one on the left and the one above. For this problem, it would be very helpful to have a table where, for each cell, we store the number of paths that lead to it. Then the solution becomes simple. We take the 2 neighboring cells, add their values, and get the answer. It's very similar to the staircase problem, but since we're working with a grid now, we need a table to remember the number of paths for each cell. Of course, the problem doesn't give us such a table, but that's fine. We can build it ourselves, step by step. Let's start with the simplest part. How many paths are there to the starting cell? Just 1. You're already standing there. Now let's look at the first row. How can you reach any cell in this row? Only from the cell on the left. There's nothing above it. That's the edge of the grid. And coming from below isn't allowed by the rules. So there's exactly 1 path to every cell in the first row. You just keep moving to the right. The same idea applies to the first column, the leftmost one. How can you reach any of its cells? Only from the cell above. There's nothing on the left. Again, the edge of the grid. And coming from the right isn't allowed either. So there's exactly 1 path to every cell in the first column as well. You just keep moving downward. Now move to the next cell. To this one, we could come from the left cell, and there is 1 path to that one already. Or we could come from above, and there's 1 path to that one. So we add them together and get 2 total paths to this cell, and this pattern continues. In general, we can write the formula like this. The number of paths to the current cell is the number of paths to the cell above it, plus the number of paths to the cell on the left. Now all that's left is to fill the grid using this formula, row by row or column by column. The important thing is to move in an order where the needed neighboring cells have already been computed. At the end, we simply look at the bottom right cell in our table. That's where the answer is stored. Clean, elegant, and most importantly, very similar to everything we already know. Now that the logic is clear, let's turn it into an actual solution. We start by creating an empty table called paths. This is just a 2-dimensional array. It has m rows and n columns, exactly the same shape as our grid. First, we fill the top row with 1s. As we already discussed, there's exactly 1 path to every cell in the first row. Next, we fill the first column with 1s as well. For the same reason, there's exactly 1 path to every cell in the leftmost column. And now we can compute all the remaining cells. So we go row by row, starting from the second row. We don't start from the very first one because the top row is already filled, and inside that loop we go column by column, also starting from the second column since the leftmost column is already handled. Together, these two loops walk through every remaining cell in the grid, and for each cell, we apply the same rule we derived earlier. We take the number of paths from the cell above, take the number of paths from the cell on the left, and add them together. Then, step by step, the table gets filled with the correct values, and by the time we finish, every cell contains the number of unique paths that lead to it, and since our goal is to reach the bottom right corner, we simply look at that cell in the table. That value is the answer. Clean, systematic, and very familiar by now. Exactly what we expect from dynamic programming. Now let's evaluate the complexity of this algorithm. First, the time complexity. Here we have two nested loops. The outer loop runs m times, once for each row. Inside it, the inner loop runs m times, once for each column. Together, that gives us O of m times n, linear in the total number of cells. Now the space complexity. We create and store a table with m rows and n columns. So the space complexity is also O of m times n. That's already quite good. But just like in the previous problem, you might notice that we can optimize this even further. Let's look at the formula one more time. To compute the values for the current row, we only need two things. The previous row, because we're taking an element from above, and the current row that we're filling right now, because we're taking an element from the left. All other rows above are no longer useful. We've already used them, and we'll never need them again. So keeping the entire table in memory is wasteful. In fact, a single row is enough. Then let's optimize the solution with that idea in mind. First, we create a one-dimensional array called row with length n, and immediately fill it with ones. This represents the first row of the grid, where there's exactly one path to each cell. Now we iterate over the remaining rows of the grid, starting from the second one. Inside that, we go through each column. For every cell, we update the value in the current row using the same formula as before. But here's the key insight. Row J still holds the value from the cell above because it hasn't been updated yet in this iteration. Row J-1 already holds the value from the cell on the left because we just updated it. So by adding these two values together, we get the correct number of paths for the current cell. The important trick here is that instead of writing results into a new row, we overwrite values in the same array. That's safe because once we move forward, we no longer need the old values. By the time we finish processing all rows and columns, the last element in this array contains the answer, the number of unique paths to the bottom right cell. And for this solution, the time complexity stays the same, O of m times n, since we still use two nested loops. But the space complexity is now much better. We only store one row, so it drops to O of n instead of O of m times n. And if m happens to be larger than m, we could just as easily store a column instead of a row. In that case, the space complexity becomes O of min of m and n. The idea stays exactly the same. We just keep the minimum amount of data we actually need. Now let's summarize the typical signs of a grid problem. First, you're working with a two-dimensional space, a table, a grid, a matrix, something with two dimensions. Second, movement is restricted. In many of these problems, you can move only to the right and downward. Sometimes other directions are allowed as well, but the number of possible moves is usually limited. Third, the state of each cell depends on its neighboring cells, specifically the cells you're allowed to come from. In this problem, for example, you can reach a cell only from above or from the left. Fourth, there are clear base cases, the edges of the grid, and those can be filled in immediately. So if you see a problem like this, the strategy is straightforward. Build a table, fill in the borders, and then compute the remaining cells using a formula derived from the movement rules. That's the grid pattern, two-dimensional dynamic programming. Now let's practice with the grid pattern and solve a variation of the previous problem on AlgoMonster. It's called Unique Paths 2. We also have a grid here, and we're located at its top left corner. And we need to find the number of unique paths to the bottom right corner, just as in the previous problem. And again, we can move either down or right. However, now there can be obstacles in the grid where we cannot move. So our grid consists of integer numbers, zeros and ones. If a cell has 0 as its value, we can move there. If it's 1, this cell is blocked and we need to find another way around it. Well, how do we find all the unique paths here? We already know the logic and the formula for finding the paths from the previous problem. We just build a grid and for each cell store a sum of the two adjacent cells, the left one and the top one. However, now we have the cells where we cannot move. What does that mean for our DP grid? It means that there are no ways at all to any cell that has an obstacle inside it. So when we meet such cell, we just put 0 in it inside our DP grid, and for others we use the same formula we had before. But here we can optimize the solution again if we create not a whole DP grid, but a one-dimensional array that stores just one row of this grid we're processing, just because we never use any other cells except the adjacent ones. With such a solution, we'd still go over all the cells of the initial grid, which would give us O of m times n time complexity, but we'd have just O of n space complexity as we store only one row of this grid throughout the solution. Let's write the code for this solution. First of all, if our starting cell has an obstacle inside it, we can just return 0 as there are no ways out of it. Then I'll create variables m and n for the number of rows and columns in the grid, just for convenience. Now we create our DP array of n elements, where we will be calculating our unique paths to every cell of the grid. The leftmost element of this array is 1, just because there's only one path to the cell where we're starting. Then we'd need to go over all the elements in the grid. For that, we create 2 loops, by rows and by columns. And inside, we first check if we came across an obstacle. In other words, the current cell contains 1 inside. If that's true, then we just put 0 in our DP array, as there are no ways at all to the cell that has an obstacle inside. Otherwise, we'd just add the number of unique paths to the cell on the left from the current, which is dpj-1 to the number of unique paths to the cell on top of the current. This one is being stored in dpj from the previous iterations, so we just use its value and save the new result to the same cell. In the end, the last element of our DP array has our final answer, as it corresponds to the bottom right corner of the grid, so we return it. Let's run the tests and check if we solved it correctly. Works good. So another problem is tackled. If you want to solve it yourself, click the link in the description of this video. Okay, we've learned how to work with grids. There was a table and we filled it cell by cell. But there are also problems where you can still use a grid-like idea to solve them, even though a grid is not explicitly mentioned in the problem description. For example, this happens when you're given 2 strings and need to compare them with each other. This brings us to the next dynamic programming pattern, 2 sequences. And now you'll see that it is also solved using a 2-dimensional table. The structure is the same, but the logic for filling the table is a bit different. Here is a very popular problem, longest common subsequence. You are given 2 strings and you need to find the length of their longest common subsequence. But before we go further, let's clarify what a subsequence actually is. It is not a substring. A substring means that the characters go one after another without any gaps. A subsequence, on the other hand, means that the characters appear in the same order, but there may be gaps between them. Take the word stone as an example. Ton is a substring, 3 consecutive characters, but toe is a subsequence. We skip the N, but the order is still preserved. First T, then O, then E. So the task is to find the longest such subsequence that exists in both strings at the same time. Let's take 2 words, stone and tower. What common subsequences do we have here? The letter T appears in both words, so that's a subsequence of length 1. The letters T and O also appear in both words, and in the same order, so that's a subsequence of length 2. What about T, O, and E? All 3 appear in the first word, and all 3 appear in the second word. The order matches, so toe is a common subsequence of length 3. Can we find anything longer? Let's check. The letters S and N from the first word don't appear in the second, and the letters W and R from the second word don't appear in the first. So the answer is 3. Toe is the longest common subsequence for these 2 words. Okay, so how could we solve this problem directly? One idea is to take the first string and generate all of its possible subsequences. Then for each of them, check whether it appears in the second string, and finally choose the longest one that does. But here's the problem, how many subsequences does a string of length n have? For each character you have 2 choices, either include it or skip it. So for n characters you get 2 to the power of n subsequences. If n is 10, that's 1024. Still manageable. If n is 20, that's already about 1,000,000. If n is 30, that's 1,000,000,000. And in this problem, strings can be up to 1,000 characters long. That's 2 to the power of 1,000 possibilities, a number with hundreds of digits. The universe will end long before our program finishes. So clearly, we need a smarter approach. In previous problems, we built a table and filled it step by step. So maybe we can do the same thing here. Remember the grid problem. There, we already had a table, the grid, and we just filled it with values. We had a vertical position and a horizontal position, and for each cell we computed the answer, step by step. Here, we don't have any table yet. We only have two strings, stone and tower. So the natural question is, where do we even get a table from? Look, to solve this problem, we need to somehow compare these strings. Not as a whole, but in parts, because a subsequence is about which characters we take and which ones we skip along the way. That means it's important to know which character of the first string we're currently at, and also which character of the second string we're at. So now we have two positions. A position in the first string, let's call it I, and a position in the second string, j. Let's take our strings stone and tower. Suppose I equals 1. That means we're looking only at the first character of the first string, s, and j equals 1. That means we're looking only at the first character of the second string, t. What is the longest common subsequence for s and t? None. The letters are different, so the answer is 0. Next, j equals 2, and we compare s and to. There is no s there, so the answer is still 0. And as we go further, s doesn't appear anywhere in the second string, so we just keep putting zeros. Now I equals 2, and we take st from the first string. We compare st and t. There is a common t, so the answer is 1. Then we compare st and to. The only common letter is still t, so the answer stays 1. And for all the other variants, only t matches in st, so we put 1 everywhere. Now the third row, we take sto. For j equals 1, we compare sto and t. There is a common t, so the answer is 1. Then we compare sto and to. Here we have both t and o, and they are in the correct order. So the answer is already 2. All other variants won't add anything new beyond to, so we put 2 everywhere. See, we're literally filling a table again. We've just built it ourselves. The position in the first string goes along the vertical axis. The position in the second string goes along the horizontal axis, and each cell contains the answer for those specific positions. And if we fill the whole table all the way to the end, then in the bottom right corner we'll get the answer for the full strings. That is the solution to our problem. But filling each cell by hand would be way too slow. So once again, we need a formula that lets us compute the value of any cell based on values we've already computed. Let's call our strings first and second. Then we'll create a table dp of size m+1 by m+1, where m is the length of the first string and n is the length of the second. Why +1? Because we need a base case, the empty string. If one of the strings is empty, what is their common subsequence? None. The length is 0. So the first row of the table is all zeros, and the first column is also all zeros. Now comes the interesting part. How do we fill the remaining cells? What does dpij represent? It represents the length of the longest common subsequence for the first I characters of the first string and the first j characters of the second string. Imagine we're standing at the cell dpij, and we're looking at the corresponding characters in both strings. And now we have two possible cases. First case, the characters match. Suppose we compare sto and to. The last letters are o and o. They are the same. That means this letter will definitely be part of our common subsequence, because it exists in both strings at the current positions. So what was the longest common subsequence before this character? That would be for st and t without the last letters. This is exactly the cell dpi-1j-1, the diagonal one, and it contains 1 because st and t share the letter t. Since we've now found another common letter, o, we just add 1 to what we already had. So we get 1 plus 1 equals 2. In other words, to compute the current cell, we take the diagonal cell and add 1 to it. Why the diagonal? Because we're consuming one character from each string. They match, so both are included in the subsequence. That's why we look at the cell where both strings are shorter by 1 character, and then increase that result by 1. Now the second case, the characters are different. Suppose we compare sto and tow. The last letters are o and w. They're different, so they cannot both be part of the common subsequence. So which result do we take? We can skip the last character of the first string and look at the result for st and tow. That's the cell dpi-1j, one row above. Or we can skip the last character of the second string and look at the result for sto and to. That's the cell dpij-1, one column to the left. We don't know which choice is better ahead of time, so we take the maximum of the two. We want the longest subsequence possible. In the end, we simply choose which formula to apply based on whether the current characters match or not. Now let's see how all of this works step by step. We create a 6x6 table. 6 rows, the empty string plus the 5 letters of stone. 6 columns, the empty string plus the 5 letters of tower. Then we fill the first row and the first column with zeros. These represent empty strings, and the common subsequence of an empty string with anything is always 0. These are our base cases. Now we go through the table cell by cell. In the first meaningful cell, we compare S and T. They don't match, so we apply the second formula and take the maximum of the left and upper cells. Both are 0, so the result is 0. That makes sense. S and T have nothing in common, so we move to the next cell. Now we compare T and T. They match, so we apply the first formula. We take the diagonal cell and add 1, and we get 1. Again, that makes sense. We found one matching letter. Then we keep moving forward. For a while, the characters don't match, so the second formula keeps copying the best value we found so far. Then we reach the cell where we compare two O letters. They match, so the first formula applies again. We take 1 from the diagonal and add 1, and we get 2. After that, we again see a series of non-matching characters, but thanks to the second formula, all remaining cells keep the best value so far. And then we finally reach a cell where we compare 2 E letters. They match, so once again we apply the first formula and get 3. Row by row, the entire table gets filled this way. In the end, the bottom right cell contains the maximum possible value, because every step was trying to grow it when possible. That's the answer. The length of the longest common subsequence, tau. Now that the logic is clear, let's talk about the code at a high level. First, we store the lengths of the strings in variables m and n, just for convenience. Next, we create a two-dimensional array dp, our table, and fill it with zeros. This directly represents our base cases. Then we use two nested loops. The outer loop goes over the first string, and the inner loop goes over the second. We start from index 1, because index 0 corresponds to the base cases. Inside the loops, we check the characters. If they match, we use the diagonal +1 formula. If they don't, we take the maximum of the upper and left cells. When the loops finish, the entire table is filled, and the answer sits in the bottom right corner. Clean and elegant. Let's quickly estimate the complexity. For the time, we have two nested loops, each iterating over one of the strings. So the time complexity is O of m times n. Now the space. We store a table of size m by n, so the space complexity is also O of m times n. For strings of length 1000, that's about 1,000,000 operations and 1,000,000 cells, which is dramatically better than the naive 2 to the power of 1000 approach. But now, let's look at the formulas again. We see here that in order to compute the current row, we only ever need the previous row, nothing else. So we don't actually need to store the whole table again. We can keep just 2 rows, the previous one and the current one, just as we've done in the grid problem already. Let's change the code then. First, we create 2 arrays, prev and current, and fill them with zeros. These represent 2 rows of the table. And inside the loop, we compute the current row using the same formulas as before. We either look at the previous row or at the left cell in the current row. Then, after finishing a row, we just swap the arrays. The current row becomes the previous one, and we move on. And at the very end, the answer is stored in prev n because of that final swap. Now the space complexity is O of n instead of O of m times n. And if one string is shorter than the other, we can even get O of min of m and n. Even better. So now let's summarize the key signs of the two sequences pattern. First, the problem gives you 2 sequences, 2 strings, 2 arrays, 2 lists, something that needs to be compared. Second, you're asked to find something in common or to count operations needed to transform one sequence into the other, a common subsequence, edit distance, or something similar. Third, you build a 2-dimensional table. One sequence goes along the rows, the other along the columns, and the base cases sit on the edges. Fourth, the transition depends on comparing the current elements. If they're equal, you use one logic. If they're different, you use another. So if you see a problem like this, draw the table where the 2 sequences intersect. Fill the edges. Then derive the transition formula based on how the elements compare. That's the 2 sequences pattern. 2-dimensional dynamic programming for comparing 2 sequences. It's very similar to the grid pattern, except that instead of a grid being given, you form the grid from 2 sequences. And once you understand this, you can solve a whole class of problems. Longest common subsequence, edit distance, shortest common supersequence, and more. The logic stays the same, only the formulas change slightly. That's the real power of patterns. To practice, let's solve the edit distance problem on AlgoMonster. We're given two strings here, and we need to find the minimum number of operations to convert one into the other. The available operations are insert, delete, or replace a character. To understand what it means, let's look at the example here. If we have two strings, horse and rose, then how can we turn horse into rose? Well, we'd need to replace H with R. That's one operation. Then we'd remove the second R and get the word rose now. That's the second operation. And then we'd remove E in the end to finally get rose. So 3 operations in total. But how do we solve this problem for any pair of strings? If we check all possible combinations of transformations, then their number grows exponentially, which is highly inefficient. So we could create a grid based on these two strings, where in each cell dpij, we'd store the number of operations to convert the first I characters from the first string to the first j characters of the second string. Just as before, we'd also add row and column for an empty string, as those are possible results too, but they also would give us the base cases. To convert an empty string to any other string, we'd need to just insert characters there. So we can fill the first row and column in the grid with increasing numbers starting from 0. Now how do we calculate the rest of the cells? Well, when considering two characters in two given strings, what are the possible scenarios? The first one, those characters match, and that means we don't need to apply any transformations to the first string. So we just take the number of operations we had for the previous substrings, which is dpi minus 1j minus 1, the diagonal cell. But if the characters don't match, we need to apply some transformation. So there will definitely be one new operation. But then we need to choose the best option from all possible transformations we could apply to the previous substrings. So we take the minimum of the diagonal, the top, and the left elements in the grid, which represent the values we'd get if we replaced, removed, or inserted a character in the previous substrings. We're definitely adding one operation here, but as we don't know what previous transformation leads to the best result, we're considering them all and choosing the minimum one. Then, in the bottom right corner of our grid, we'd have the final answer, as it lies on the intersection of the last characters of the full strings. For such a solution, we'd create a grid, which gives us O of m times m space complexity. And then we'd need to go over all the cells in this grid to calculate this value. This gives us O of m times m time complexity too. Now let's write the code for this approach. First, I'll create two variables to store the lengths of two given strings. Then we need to create our dp grid for storing the edit distances between all the substrings. But we'd add one to the number of rows and columns, as we also need to store values for empty strings. The first column and the first row of this grid need to be filled with increasing numbers starting from 0. So we just write two loops for that. And now we can calculate the rest of the cells. To go over all of them, we need two inner loops, and inside we use the two formulas we defined before. If we have two matching characters in both strings, then we don't need to apply any new transformations, so we can just reuse the number of them for the previous substrings. That one is stored in the diagonal element. Otherwise, if the characters don't match, we apply the second formula. We add one transformation and then choose the minimum of all the possible operations for the previous substrings. In the end, we return the value of the bottom right cell of the grid. This is our answer for the two full strings. Running the tests, and we see that our solution is correct. Amazing! But this problem can also be solved recursively. You can check the solution breakdown on the AlgoMonster platform. Just click the link in the description. Okay, we've learned how to compare two strings. But what if you have just one string and you need to find something special inside it, like a palindrome? That's where the next dynamic programming pattern comes in, interval dp. And you'll see that it's actually very closely connected to what we already know. Here's a very popular problem. Longest palindromic subsequence. You're given a single string and you need to find the length of its longest subsequence that reads the same in both directions. That's what we call a palindrome, a word or phrase that reads the same left to right and right to left. ABBA is a palindrome, radar is a palindrome, but hello is not. And remember, a subsequence means the characters stay in the same order, but they don't have to be next to each other. We've already worked with this idea before. For example, in the string modem, there is a subsequence mom, and that subsequence is a palindrome. So our task is to find the length of the longest palindromic subsequence in the given string. So how could we solve this in a brute force way? In theory, we could generate all possible subsequences of the string. Then for each subsequence, we'd check whether it's a palindrome. Finally, we'd take the longest one among all palindromes. But here we fall into the same trap as before. How many subsequences does a string of length n have? Exactly 2 to the power of n. That means this approach is incredibly slow, so we clearly need something smarter. Let's notice something very important. A palindrome reads the same from both ends. That means the first character must match the last one, the second must match the second to last, and so on. Take the word radar. Why is it a palindrome? The first letter R matches the last letter R. Good. What's between them? Ada, and that's also a palindrome. The first A matches the last A, and in the middle there's just D, which is a single character, and any single character is a palindrome. Do you see the pattern? A palindrome is made of two matching outer characters and a palindrome inside them, and this observation changes everything. Now we know that to find a palindrome in a larger part of the string, it's enough to know the answer for a smaller part. Suppose we have the word total, and we want to find the longest palindrome in the whole string. We look at the ends, T and L. They're different, so these two letters cannot both be part of the palindrome at the same time. So we have two options. Either the best palindrome lies in tota, without the last letter, or the best palindrome lies in odal, without the first letter. If we already knew the answers for these two parts, we'd just take the maximum of them. That's it. Take the part tota. Again, the outer letters don't match, so they also can't both be in the palindrome at the same time. We again have two options. Either look at tot or at oda. Take the part tot. The outer letters T and T match, so both will be included in the palindrome, and between them is O, a single letter, which by itself is the palindrome of length 1. That's our base case. It's always true for any single character. Then we add 1 and 2 for the two outer letters and get 3. That's the length of the palindromic subsequence. If we do the same check for the interval oda, the best we can get there is 1, because there is no longer a palindrome. So now, going back to the interval tota, we see that inside it we have only these two possible subintervals. So we choose the better of them, and it turns out that inside tota, the best palindromic subsequence length is 3. And now, when we look at the whole word, it also has only two possible inner intervals. Again, we take the best of them, so we get that 3 is the length of the longest palindromic subsequence in the entire string. Done. And the main thing is that instead of 2 to the power of n subsequences, we now work with intervals. And how many intervals can a string of length n have? An interval is just a pair of numbers where I is the start and j is the end. The start can be from 0 to n-1, the end from the start to n-1. In total, there are about n squared over 2 such pairs. For a string of length 1000, that's around 500,000 intervals, while the number of subsequences would be 2 to the power of 1000, a number with 300 zeros. The difference is enormous. And the key point, if we compute the answer for every interval, then the answer for the whole string is simply the interval from the beginning to the end. It covers the entire string. So we'll create a table where for each interval from I to j, we store the answer, the length of the longest palindrome in that interval. We'll fill it step by step, starting from small intervals and using them to compute larger ones. Let's see exactly how. In each cell of the table, we store the length of the longest palindrome in the interval from I to j. Let's start with something simple. What's the longest palindrome in an interval of length 1? Any single character is a palindrome. These are our base cases. We can already fill the diagonal of the table with 1s. Now for bigger intervals. How do we compute the length for an interval of length 2 or more? We look at the outer characters of the interval in our string. First case, they match. For example, the interval tot. If the outer letters match, they will definitely be part of our palindrome. That's already plus 2 to the length. What about the substring between them? To define this inner interval, we move the left boundary one step to the right, I plus 1, and the right boundary one step to the left, j minus 1. That gives us the cell that stores the length of the inner interval. In this case, it's the letter O, which is our base case. We take that value and add 2, since in total the two outer letters match. That's our formula, the cell for the inner interval plus 2 for the matching outer letters. But there's the second case, when the outer characters are different. For example, the interval tal, the outer letters are T and L. Different. They cannot both be part of the palindrome at the same time, so we need to try without one of them. So either we remove the left character and look at the inner interval. Removing the left character means shifting the left boundary to the right, I plus 1, while keeping the right boundary the same, j. That's all. Or we move the right boundary, j minus 1, and keep the left as is, I. That's TA. Which of these is better? The maximum one. And that gives us the formula for the case when the outer characters don't match. And you remember that in the grid problem we went row by row, top to bottom. But here, that won't work. Look at the formula. To compute dpij, we need dp I plus 1 j minus 1, the value for a smaller interval inside the current one. This means we must first compute all small intervals, then slightly larger ones, then even larger ones. We're not going row by row in the table, we're going by interval length. First, all intervals of length 1. That's the diagonal, all 1s. Then all intervals of length 2, then length 3, and so on till we fill the whole table. Now, let's talk through the solution logic step by step. First, we store the length of the string in the variable n for convenience. Then, we create a two-dimensional array dp and fill it with zeros. This is our table. At the same time, we go along the diagonal and put ones there, because each character by itself is a palindrome of length 1. And now the main loop. First, we iterate over interval lengths from 2 to n. This is how we ensure the correct order. First, we compute all small intervals, then larger and larger ones. Then the inner loop goes over all possible interval starts for the current length. We are checking all possible intervals of a specific length, and they will start at different characters. And at each step, we also need to know the end of the interval, j. We can compute it like this since the start of the interval is I and its length is len. Now we check. If the outer characters match, we apply our first formula. Take the diagonal cell and add 2. Otherwise, if the characters are different, we use the second formula. We take the maximum of the two neighboring intervals. And when all loops finish, dp0n-1 will contain the answer, because the interval from 0 to n-1 is exactly the whole string. That means this cell stores the longest palindrome for the entire string. Now let's estimate the complexity. For the time, we have one loop over interval lengths and one loop over interval starts. Both run up to n, so the total time complexity is O of n squared. And for the space, we store a table of size n by n, so the space complexity is also O of n squared. For a string of length 1000, that's about 1,000,000 operations and 1,000,000 cells, which is vastly better than the naive approach. But look at the formulas again. To compute the current row, we need values from that same row, since I stays the same, and from the next row, where I is increased by 1. So at each step, we are again using only 2 rows in the calculations. The previous ones are no longer needed. That means we can store only 2 rows instead of the entire table, so we can optimize the code. Now we create 2 arrays, cur to store the current row of the table, and prev for the previous row. We initialize them with zeros. Now we go over the rows from bottom to top, from n-1 to 0. Why from the bottom? Because the ith cell depends on I plus 1, so we must first compute the lower rows. For each position I, we set current cell to 1. This is exactly the diagonal element in the current row, as if we had the full table. Then we iterate over all possible interval ends for the start I. That is, the loop over j starts from I plus 1 and goes to the end of the string. These two loops together iterate over all possible intervals we have, and inside we applied the same formulas for each interval. Only now, when we need to access the row below, we use the prev array, where that row is stored. And when it's time to move up to the next row, we swap our arrays so that the current row becomes the previous one. Then we continue computing for the next intervals. The final answer will be in prev n-1, because after the last iteration, we swapped them. And now the space complexity is O of n instead of O of n squared, since we store only 2 rows, not the entire n by n table. We've effectively cut it down along one dimension. Let's highlight the signs of the interval DP pattern so you can solve any task that uses it. First, in such problems, we work with a single sequence, not 2, a string, an array, just one structure. Second, usually we need to find an optimal result for an interval inside this sequence, from position I to position j. Third, the result for a large interval depends on the results for smaller intervals inside it, that is, either the left or the right boundary moves, or both. Fourth, we fill the table by interval length, not row by row, first short intervals, then longer ones. Fifth, base cases are intervals of length 1, or sometimes 0, so if you see a problem where you need to optimize something inside one sequence by analyzing its parts, that's interval DP. Examples of other problems using this pattern: palindrome substrings, burst balloons, coin game. The logic is the same everywhere. You build the table over intervals and fill it from smaller to larger ones. To practice, let's solve the palindromic substrings problem on AlgoMonster. We're given a string here, and we just need to count how many of its substrings are palindromes. So, there are n squared possible substrings in a string, and if we check each of them for being a palindrome, we'd get O of n cubed total time complexity. But using the interval DP pattern, we can solve this problem more efficiently. From the previous problem, we know that in a palindrome, the first and the last characters match, and the intermediate part also forms a palindrome. So if we know that the intermediate interval is a palindrome, and the last characters in the substring match, then we can calculate in constant time that the substring from I to j is also a palindrome. Then we can just check all possible substrings and run a recursive function for each of them that checks their first and last character and then executes itself for an inner interval between them. And it does that until it reaches an interval of just one character, which is always a palindrome. That's our base case. Whenever our recursive function returns true, we increment the total counter of all the palindromes. And to not repeat the calculations for the same intervals of larger substrings, we'll use memoization. As you see, interval DP problems can also be solved recursively, and sometimes it's easier than creating a grid. This solution gives us O of n squared time complexity, as we need to check all the substrings. And thanks to memoization, we don't need to repeat any calculations and do them only once. And for the space, we use memoization and store the result for each possible interval, which gives us O of n squared space complexity. Let's now implement this approach. First of all, we need the LRU cache for our future memoization. Then I'll create a variable storing the length of the given string, just for convenience. Our initial palindrome counter is 0, and then we just create 2 inner loops for checking all the substrings in the given one. Inside, we'll run our recursive function, which we'll implement in a moment. If that one returns true, we just increment the total counter of palindromes. In the end, we'll return that counter. But now, how does our recursive function look? It accepts the start and end indexes of an interval being checked for a palindrome. If the indices match, or the start one is greater than the end one, then it's a base case, just an interval of one character, so we return true. Then, if the first and the last characters in an interval don't match, that's definitely not a palindrome. So we return false here. Otherwise, we just run the palindromic check function for an inner interval, which is from I plus 1 to j minus 1, and return its result. The last bit is to add memoization. It's easy in Python. We just add the LRU cache annotation to our recursive function. Perfect. Let's run the test to make sure that our solution is correct. And it works! You can also check how this problem may be solved using the bottom-up approach. Just click the link in the description. Okay, we've learned how to work with intervals, but there was one special thing there. To compute the answer for an interval, we only needed neighboring intervals. Sometimes though, to compute the current element, you don't just need a couple of neighbors. You may need to check all previous elements. That's the next dynamic programming pattern, non-constant transition. And now you'll see how it's different from everything we've done so far. Here's a popular problem. Longest increasing subsequence. You're given an array of numbers, and you need to find the length of the longest subsequence in which every next element is strictly greater than the previous one. A subsequence is when elements go in the same order as in the original array, but not necessarily consecutively. We've already seen subsequences in previous string problems. For example, in this array, the subsequence 1, 2, 4 is increasing. Each next element is greater than the previous one, but 3, 5, 4 doesn't work because 4 is less than 5. So we need to find the longest such increasing subsequence. In this case, the answer is 3 because that's the maximum length for this array. How would you solve this head-on? Again, you could generate all possible subsequences of the array. For each one, check if it's increasing or not. Then find the longest among the increasing ones. But here we fall into the same trap as before. How many subsequences does an array of length n have? For each element, you have 2 options. Either it's in the subsequence or it isn't. So again, there are 2 to the power of n possibilities. That means such an algorithm would run forever. But let's think about it differently. We'll build an increasing subsequence step by step, adding one element at a time. Suppose you're looking at some element of the array and want to add it to a subsequence. When is that possible? Only if it's greater than the last element of the sequence you already built. For example, you have the sequence 1, 2. The last element is 2. Can you add 4? Yes, 4 is greater than 2. You get 1, 2, 4. Then, can you add 1? No, 1 is less than 4. The sequence would stop being increasing. That's the key point. To extend an increasing subsequence, the new element must be greater than the last one in it. Now, let's think in dynamic programming terms. We already know a lot. As usual, we'll create an array dp, where each cell will store the length of the longest increasing subsequence that ends at index I. Why ends at I? Because when we want to extend some sequence, it's important to know what it ends with. Only then can we understand whether we can add the new element. And here, we don't need a 2D table, because we're moving in one direction. A simple array is enough. Let's start with something simple. What's the longest increasing subsequence that ends at the first element of the array? Just that element itself. One element, length 1. Same for any element, which itself forms a subsequence of length 1. So initially, all cells of our DP array contain 1. That's our base case. Now the fun part, how do we compute the lengths for the other subsequences? Look closely. In the staircase problem, we looked at 2 previous steps. In the grid problem, at 2 neighboring cells. In the palindrome problem, at neighboring intervals. There was always a fixed number of dependencies. What about here? Let's look at our array and go step by step. We go left to right. We check whether element 1 can form an increasing subsequence with the previous elements. There is exactly 1 previous element, 3 at index 0. Since the subsequence must be increasing, we check. Is the previous element smaller than the current one? No, 3 is greater than 1, so we can't extend the sequence ending at 3 with 1. It would stop being increasing. No suitable candidates, so DP at this position stays 1. Then we look at element 5. It could form a subsequence with any of the previous elements, 3 or 1. First, we check the increasing condition for 3. Is 3 less than 5? Yes, so we can extend the sequence ending at 3. How do we compute the new length at this element? We take the best length for that previous element from DP, since that's the end of the subsequence, and add 1, because we're adding 1 more element to the subsequence, 5 in this case. We get this formula, but we can't stop yet, because we have a second candidate subsequence that we can extend with 5, and we must check it too because it might turn out longer. We check, is 1 less than 5? Yes, we can also extend the sequence ending at 1. Then we take its current best length from DP and add 1. Again, we get 2. So we used both variants. We need to pick the maximum because we're looking for the longest subsequence. Since they're equal, we store 2 for 5. The key point is, we had to check both previous elements. You might think this feels like the staircase problem. Just look at the 2 previous options, pick the maximum, and move on. But watch what happens next. Now we need to compute the length for element 2. It already has 3 previous candidates. Any of the previous numbers can potentially form a subsequence with it. We must check them all because in theory, any one of them might give the best result, not just the last 2. So we compare 2 with each of the previous elements, and if it's larger, we compute our formula. Then take the maximum among all valid options and store it in DP for this element. Then we go to the next element, and now we'll have to compare it with 4 previous elements, not just 2, and pick the best option. See what's happening? At each step, the number of checks grows, and we couldn't know in advance which previous element would give the best result. The 3 at the start, the 1, the 2 in the middle, we had to check them all. And this is fundamentally different from all the previous problems. Before, to compute the next result, we used a specific limited number of previous results. Here, to understand which subsequence we can extend with the next element, we need to check all previous elements. Any previous element might be the end of some subsequence that we can extend with the current one. Which previous element do we choose? The one that gives the maximum length. So we get this formula. We iterate over all previous elements before the current one and compare each with the current element. If nums j is less than nums I, we can build an increasing subsequence. Then we take the current length for that subsequence dpj and add 1 for the new element. And because we need the best option among all previous candidates, we take the maximum between this new value and what we already had in dpi. Now that we have the formula, writing the code is easy. Let's go through it step by step. First, we store the length of the original array in the variable n for convenience. We create our dp array and immediately fill it with 1s to set up the base case. Now we iterate over all elements that will try to attach to previous subsequences. We start from the second element because the first one has no previous elements to compare with. Then comes our formula. We iterate over all elements before the current one, compare each with it, and if nums j is less than nums I, we add 1 to the length of the subsequence ending at j. Then we take the maximum among all values we've computed so far for this I. The final result will be stored in one of the cells of the dp array. We just take the maximum from dp. That's the length of the longest increasing subsequence. Now let's estimate the complexity. Time. The outer loop runs n times. The inner loop runs on average about n over 2 times. Overall, it's O of m squared. Space. We create a dp array of length m, so it's O of m. Even though we have quadratic time complexity, this is much better than the exponential complexity of the naive approach. It's a huge performance improvement. We can't really optimize memory further here like in previous problems because at each step we need to check all previous dp values. So we can't store less data. Quadratic complexity is okay, but for very long arrays, we'd like something faster. And there is a way. You can solve this in O of n log n using binary search, but that's a completely different technique that goes beyond DP patterns. Let's highlight the signs of the non-constant transition pattern. 1. The state dpi depends not on a fixed number of previous states, but on a variable number, sometimes on all previous ones. 2. You need to iterate over several or all previous candidates and pick the best, usually a maximum or minimum minimum. 3. You get a nested loop, the outer one over the current position, the inner one over all candidates. 4. Time complexity is usually O of n squared because of the two nested loops, although sometimes you can speed it up with special data structures. 5. Memory optimization is usually impossible. You need all previous values. If you see a problem where, to compute the current state, you have to loop over and compare several previous ones, that's non-constant transition. Here are some examples of other problems. Longest botonic subsequence, maximum sum increasing subsequence, box stacking. The idea is the same everywhere. Iterate over all candidates and choose the best one. Let's practice with this pattern on AlgoMonster, solving the problem called partition array for maximum sum. Here we are given an array of integers in an integer k, and we need to partition this array into subarrays of lengths at most k. But after we do that, each element in every subarray will be replaced by the max value of that subarray, and we need to return the largest possible sum of the whole modified array. Let's look at the example. If we have this array and k equals 3, then one of the ways to partition this one is to split it into these two subarrays. In this case, in each subarray, every element is replaced with the max one. That is 15 in the first one and 9 in the second. Then the original array becomes like that because its partitions were updated this way, and by adding up all its elements, we get 72. This is the answer. And the thing is that there may be multiple ways to partition this array, but we need to find the way that gives the maximum sum. Well, how do we solve that? Basically, we know that our subarrays must be contiguous, so there will definitely be some final subarray, right? It may be of length from 1 to k, yes, but if we fix that last partition, the rest becomes an independent subproblem. For example, for our original array and k equals 3, we could have these last subarrays potentially, and each of them gives us these remaining subproblems. So if we knew the best answer for each subproblem, then we'd just pick the right combination of them, and that's it. And that leads us to the DP solution. If we create a DP array where at each element we store the max sum achievable by partitioning the first odd elements of the original array, then for DP6, for example, we can say that it's the previous sum plus the maximum from all the last partition options we can have here. If we're looking for DP6, then we have 3 options of the last partitions. If it's one element, then our formula is DP5 plus this one element because it's the max one in such a partition. Or we could have a partition of length 2. Then to find DP6, we take DP4 and add the maximum of those 2 elements twice because there are 2 elements in the partition and they are all being replaced by the max one. And for the third option, there's the same logic. We take DP3 and add the max partition element 3 times to it. So in the end, to find DP6, we basically take the maximum one of these 3 options. And this formula generalizes for every I. We take all the partition lengths possible in a loop and then add together the previous sum before that partition and the max element of that partition multiplied by its length. And if we go with such a solution, we'd create a DP array of length n, which gives us O of n space complexity. And as we loop through all the elements and all the possible lengths of partitions where k is the maximum one, we'd get O of n times k time complexity. So let's write the code for this one. It's quite short, in fact. First, I create a convenient variable for storing the length of our array. Then let's create our DP array. Now we can loop through all its elements. Inside, we need a variable to store the maximum element per partition. Just convenient. Then we start a loop over all possible partition lengths till k or the current element because we can be at the beginning of the array and won't be able to look back too far. That's why we minimize the length here. Then inside a partition of a given length, we find the maximum element and store it in our variable. It's convenient here that we don't need to scan an entire partition looking for the max element all the time. As we increase the partition length by 1 on every iteration, we can just take the best option from the previous maximum and the new element in the partition. That's important so we don't get another k multiplier in our time complexity. And then we just apply our formula. We just take the maximum from the partition sum we've been able to find so far, and the previous sum for the current partition, plus the max element of this partition multiplied by its length as all the elements are replaced by it. And in the end, the last element in the DP array contains the answer for the problem. Let's run the test to make sure we've got it right. And it works. The link to this problem is in the description too. Okay, we've learned how to work with subsequences in an array of numbers. But what if now we need to build a specific sum from the elements of this array? That's the next dynamic programming pattern, knapsack-like problems. Here's a popular lead code problem. Partition equals subset sum. You're given an array of positive numbers, and you need to determine whether it can be split into two parts so that the sum of elements in both parts is the same. Let's look at a concrete example. Here's the array. Can we split it into two equal parts? Let's compute the total sum. 1 plus 5 plus 11 plus 5 equals 22. That means each part must have a sum of 11. So, can we get 11 from these numbers? Look, 1 plus 5 plus 5 equals 11. Great. What's left? The number 11. Also 11. So from this array, we can indeed form two groups that have the same sum. And the answer to the problem is yes, or true. Now, another example. The total sum of all elements here is odd. And if it's odd, we can't split it into two equal parts. Half of 11 is 5.5, and we only have integers. So the answer is no, false. And we can see that immediately without checking all combination. Okay, how do we solve this problem in the general case? The simplest way is to generate all possible subsets of the array. For each subset, we compute the sum and check if it equals half of the total sum. If yes, that automatically means all remaining elements form the second half of the sum. So we found a solution, but we hit the same problem as before. How many subsets does an array of length n have? For each element, there are two options. Either it's in the subset or it's not. So again, 2 to the power of n options. Far too slow. So let's think differently. We don't actually need all subsets. We just need to know, is it possible to get a specific sum? Imagine you're packing a backpack. You have items of different sizes, and the backpack has a fixed capacity. No more, no less. Question: can you fill the backpack exactly without any remaining space using some of the items? That's the classic knapsack problem. And our problem is a special case of it. Here we have numbers. These are our item sizes, and we have two backpacks of the same capacity. We need to know whether we can distribute the items between these two backpacks so that both are filled completely and all items are used. When is this possible? Only if the total size of all items can be split into two equal halves. Then each backpack must hold exactly half. But here's the fun part. We don't actually need to try to fill both backpacks. If we can fill the first one exactly to half of the total sum, the second one is automatically filled by all remaining items. Their sum will be the other half. Now let's think in dynamic programming terms. We need to check whether we can build the sum 11 from the array elements. Let's think about how we build sums in general. Take the first element, 1. What sums can we build now? Only 0 if we don't take anything, and 1 if we take that 1. Add the next element, 5. Now we can build 0, 1 as before if we don't take 5, and also 5 and 6 by adding 5 to the old sums. Notice that we don't duplicate 0 and 1 because we don't care about different ways to get them. We only care whether they are possible at all. If we can get them in different ways, great, they just stay. But new sums, we add. So with each new element, our set of reachable sums grows. We can either take the new element, then we get new sums based on existing ones, or skip it, then previous sums remain. And each next sum can be computed only from previously computed sums. These are all the variants we've managed to build so far in one way or another, and then we try to add the new element to each and see what we get. We hope that one of the new sums will be the target. So we can apply dynamic programming here as well, because if we now add the next element, we'll again iterate over all past sums that were possible with previous elements and get more sums that include the new one. And one of them might be 11. That's exactly what we're looking for. So we need a way to store all previously reachable sums, and most importantly, avoid duplicates. If we keep storing duplicates, we'll end up with more and more repeated sums and again blow up to exponential complexity. The trick is to avoid duplicates so we don't do repeated work for each new element. In previous problems, we used an array where indices matched element positions in the original array, and in the cells we stored intermediate values for that element. But here that's not convenient because for each element we get not one but several possible sums. We can't store them all inside a single cell. You might say we could use a 2D array, but then how do we eliminate duplicates nicely? Also not great. Here's the key idea. What if we create an array where the index is the sum we can build? Then we make an array that has every index up to our target sum inclusive. Each cell stores true if this sum is reachable and false if not. So index 0 answers whether sum 0 is possible, index 5, sum 5, and so on. Then whenever we discover a new sum, we just flip its flag to true in the array. And it's fast because we have direct access by index. If we see the same sum again later, we look into its cell, see true, and leave it as is. No new entry is added. Now to find the answer, we simply look at the cell with index index 11. If after all computations it's true, then we can build sum 11 from some elements of the array. And we don't care which exactly. But how do we fill this array? That's where our earlier observation comes in. New sums are built from already reachable ones. Look closely. This is the key moment. Let's take our first example. Target sum is 11. We create an array from 0 to 11, 12 elements in total. Initially, all values are false except index 0, because sum 0 is always reachable if we take nothing. All other sums haven't been built yet, so they're false. Now we go through the input array and add each element into our reachable sums. Take the first element, 1. We look at the sums we can currently build. We can always build sum 0. Then we add 1 to it. We get a new sum. And we mark that index as true. If we go further, all other cells are still false, so nothing else changes. Take the next element, 5. We start iterating over our sums. Sum 0 is true. We add 5 to it and get sum 5. Mark it as reachable. Next, sum 1 is also true. We add 5 to it and get sum 6. Mark it as reachable too. So we've got 2 new sums, but all previous ones also remain in our array. We might need them later to build other sums. Take the next element, again 5. Which sums were reachable? We could build 5 and 6, and they're still there. But now we can also build 10 by adding 5 plus 5. And we can build 11 by adding 5 plus 6. At this point, the last cell becomes true, which means we've reached our target. See the pattern? For each element, we update our sums array like this. If we could previously build sum s, then now we can also build sum s plus num. The current value stays true if it was already true, or it becomes true if we can now reach that sum by adding the current element. But unfortunately, this formula doesn't work as is. There's a very important detail. Let's go back to the moment when we're processing the second element in our array, 5. If we use this formula, we start moving left to right through the sums array. We take 0, add 5, mark that sum. Then we take 1, add 5, mark that sum. So far so good. But our loop must continue, because for each element we have to check all possible sums. There might have been larger sums before that could give us larger values forward. So we keep iterating. We go over element by element, most cells are false so nothing changes. Then we reach index 5. It already stores true. We use it, add 5, and get 10. But here's the problem. This cell represents a sum we just computed using the very element we are currently processing. So we already added this element once, and now we're adding it again. That's not allowed by the problem. Each array element can only be used once. So if we write the update formula while moving left to right, we run into this issue. How do we fix it? We simply go from right to left instead. Since adding a number always produces larger sums, all newly computed ones appear to the right, while our movement is to the left. That means we will never touch these new values again in the same iteration. To do that, we slightly change the formula and run the loop from larger sums to smaller ones. Now let's write the code to make sure everything is clear. First, we compute the total sum of all elements in the array. Then we check if the sum is odd, we immediately return false. It can't be split into 2 equal parts, so we can't have 2 equal backpacks. Next, we divide the total sum by 2. This is our target sum. You can think of it as the capacity of one of the 2 backpacks we want to fill. Then we create our sums array and initially fill it with false. We set index 0 to true, because sum 0 is always reachable. Then we go through each number in the original array. That's the outer loop. For each number, we need to walk through the sums array and update it from right to left. This is the trick that prevents us from using the same element twice. So we start the inner loop at the target sum and go down to the current element. Why? Because in the formula, we subtract the current number from the sum. The last index minus num should reach 0. This way, we cover all valid sums up to the target. In the end, we return the value of the last cell in the sums array. If it's true, the array can be split into 2 equal parts. That's exactly the answer we need. Now let's estimate the complexity. Time. The outer loop runs n times, once per array element. The inner loop runs up to target times, and target is at most half of the total sum of all elements. In the worst case, that's O of n times sum. Space. We create a sums array of size target plus 1, so O of sum. That's much better than the naive exponential solution. Now let's highlight the signs of knapsack-like problems. First, you need to build a specific sum or reach some target value from the elements of an array. Second, each element can be used a limited number of times, usually exactly once. Third, the order of elements doesn't matter, only the combination does. Fourth, you create a DP array where the index is a possible sum and the value is whether it's reachable or what maximum or minimum you can get. Fifth, you iterate over the array elements. For each one, you update DP from right to left, if the element can be used once, or from left to right, if it can be used unlimited times. If you see a problem where you need to build a sum or check whether some value is reachable from a set of numbers, that's a knapsack-like problem. Here are some examples of other problems following this pattern: coin change, target sum, last stone weight 2, ones and zeros. In all of them, the idea is the same. You build an array of reachable values and update it element by element. For the practice, let's solve the coin change problem on AlgoMonster. We're given a list of integers called coins, and its values represent different coin denominations. Also, we're given a total amount of money, and we need to find the fewest number of coins to make up that amount. For example, we have coins of 1, 2, and 5, and we need to make up 11 with them, and the answer will be 3, because we can take 2 coins of value 5 and also 1 coin of 1. That's 3 in total. And to solve this problem, we can again create an array where each element number represents the sum we can collect, but the value of an element contains the minimum amount of coins needed for this sum. So if we need to get 11 with these coins, then we create an array where the 11th index is the last one. And the base case would be 0 because we need 0 coins to get the sum of 0. Then we go over this array, and for each element we consider all the coin denominations we have. If we want to get the amount of 1, which is our index here, then what coins could we use? Only the coin of 1. So we look back at the previous sum without this coin, which is 0, and just add 1 coin to it. But here's where it gets interesting. When we try to collect the amount of 2, which is this index, we can get it in 2 ways. We can use a coin of denomination 1. For that, we just looked at the previous sum without this coin, which is DP1. But also, we could use a coin of denomination 2. So we'd look back at the previous sum without this coin, which is DP0. And then we'd take the minimum value of those two, because we're minimizing the number of coins we need, and add 1 to it because we're adding 1 more coin to the previous sum. And then we move on. For 3, we again can use only coins of 1 or 2. We cannot use 5 because it's too much to get 3. So we again take the minimum of 2 previous values without these 2 possible coins and add 1 to that. And only when we get to the amount of 5 can we consider all of the available denominations now. So we're taking the minimum of the 3 previous values now. And then we move on with the same formula, subtracting the available coin denominations from the current amount we're targeting and choosing the minimum from the previous sums. This way, when we get to the last element, which is our target amount according to the problem, we have the minimum amount of coins for that one too, because we've been minimizing it all the way here, and this is our answer. Solving it this way would require creating an array of amount elements, which gives us O of amount space complexity, and we go through all the elements of that array, where for each element we also check all the coin denominations. That gives us O of n times amount time complexity. Now writing code for this one is easy as we've got the formula. First, let's check a base case. If we need to collect the amount of 0, there are 0 coins needed. Now we can create our DP array and fill it with infinities because we'll be minimizing values in those cells. As we said, to get the amount of 0, we need 0 coins. So that's our base case in the array too. And now we can run a loop over all the elements of this array, and inside we'll also be looping through all the coins we have. First, we check that the coin is not too big, and we can actually look back at the previous sums with that one. And then we just use our formula, take the minimum of the previous sum without this coin plus this coin, and we compare it with the number of coins currently stored in this cell, because we might have got a better value with a different denomination already. In the end, we just return the value in the last element of our array, or -1 if we haven't been able to collect this amount with the given coins. Let's run the tests. Works perfectly. So you can now go to the AlgoMonster and solve this problem yourself. I hope you liked the video. If you want to practice more with DP or any other coding techniques, please check out AlgoMonster portal using the link in the description. There are plenty of detailed explainers and other problems you can practice on. Thank you for watching, and I'll see you in the next one.